Greetings, I'm Matthew Von-Maszewski with RocksDB. As a quick plug, RocksDB is a database that allows you to work on documents, graphs, and key value stores simultaneously in a cluster. And it's in a cluster part that brings me here today. RocksDB is now a backend to RocksDB, a storage engine. We added it just this year. It is, as you know, a derivative of Google's LevelDB. And I've worked with LevelDB and 3 other derivatives, RocksDB being the most recent that I've worked with. If you think of nothing else from this presentation before you leave, you need to focus on the fact that everything about LevelDB, RocksDB, all of the other derivatives is they are optimized for an environment that may not be yours. And I got news for you, it's not ours. But keep in mind, Google's DB started off, we're going to optimize this for a cell phone. Honestly, there's no joke about that. And you have, as you listen to the guys here at RocksDB and you look at this webpage wikis, you can tell that, hey, this is optimized for really high-end servers. So what happens if you're not in one of those 2 environments? Well, let's look at an output from a really high-end server that kind of matches what you see on the performance output pages of the wiki for LevelDB. This is a server that has 32 cores, 128 gigs of RAM, and 1 Fusion IO PCI drive card, which means we're doing a storage device on the PCI bus. We're not doing anything spinning. We're not even doing SSDs. This is really fast stuff. Now, this may not look like high numbers to you, but because I've pulled all of the optimizations out of RocksDB running on this one server, so all I can do is see what is the impact solely of RocksDB. You see it starts really fast, it kind of slows down, and we got some low-hanging ones here. But I got news for you, these low-hanging ones are self-inflicted wounds that we'll talk about also in a few minutes. But that is the RocksDB environment for Facebook. Let me talk to you about our customers that use AWS. As you look, this line is kind of smaller, but you expect that, right? Because this AWS is 4 cores, not 32. 32 gigs of RAM, not 128, and spinning SATA drives. Okay, it's a lower cost machine. That's great, right? But what really is not great is these guys that are hanging out right here on the 0 line. These are 10-second intervals of 0 data being written. And in fact, one of these adds up to 110 seconds of 0 data being written. We have a cluster. So first off, this means that from a user standpoint, if there have one user who his client will do a write, time out at 10 seconds, and then retry 5 more times, then it just aborts. And so if anything gets over 60 seconds without a positive reply, his program aborts. We're right here at 110. Not good. Now, if you also think about it, 120 seconds is TCP timeout, which means you can lose a connection. This got a little worse. In the case of our database, we have a cluster, and that 110 seconds, if we do an operation that requires all cluster members to be a participant, and one of those guys hits the 110 seconds, whole cluster stalls 110 seconds. So this is the difference between having a Facebook machine and having an AWS machine. So that's why I said you've got to keep in mind environment. Now, when I start talking about why this is happening, I don't know how many of y'all really know what goes on underneath the cover. So I'm going to do a quick presentation of that. So when I'm talking about sections, you know really what I'm dealing with. You're going to do a write. Typically, the write goes into what's known as the write buffer, and it gets written to the recovery log, also known as the wall table, wall file, whatever you want to call it. And once you fill up this write buffer, it moves down to become the old write buffer, which in the Google parlance was the immutable memory. And then after a while, that flushes, flush being the Facebook term, down to a level 0 SST file. Now, the key points here are, if this guy doesn't flush before this one fills up, everything stops. Writes just stop until this clears out all the way to the disk. Now, the second thing that can happen is if too many level DB level 0 files accumulate, that number's kind of controllable, everything will stop until we clear this out and make room at level 0 for level 1. Now, after that, there's really no one gives a shit whether you keep up on any of the other levels. That's got its own problems, but we're not solving those here today, okay? So, now this guy right here, RocksDB has given you a great tool, and you need to be using it. They give you a parameter that says, how many old write buffers can I still have in memory before we go and stop, before we call this really bad? If you're using column families, that number needs to be number of column families plus 2. That's the second thing you want to take out of this if you decide to go to sleep now. All right? Because, remember I was talking about we have some self-inflicted wounds? Right here. Okay. Everything from here, kind of average where my pointer is, right? Everything from here down, that's all because the column families are flushing together. And we have 3 column families that are active at one point, and they're flushing together. So that puts 3 write buffers on the list to go out the door, and we have the standard, the default setting of 1. That means the system just stops writes. Not because we're behind, but because we flushed all of them at once, and we said, hey, if there's more than 1, stop. So now we have it set to our number, which actually is a total of 7, plus 2, which is 9. And guess what? That all goes away. So that's a self-inflicted wound. But that doesn't really explain everything that's going on here. What's going on here is also because we have only 4 cores, and these take time. It takes time to move all this over to process one of these. You've got to read the file, you got to decompress the file, you got to calculate the CRC, you have to then write it to the new guy, which means you have to compress it, you got to calculate the CRC, put it on the disk. All right, and of course, self-inflicted wounds. So, we've addressed this initially. Okay, first off, this is the same graph we just saw with the black a minute ago. I've just changed the scale on the y-axis so we can focus on what's going on down here. We wrote a piece of code to do that because most of our customers actually, believe it or not, are using AWS-like servers. And of course, one of the answers you could say to them is, you just need a bigger AWS server. I kid you not, one of the guys says, we spend $400,000 a month with AWS. Our plans right now are how to make it smaller, all right? We want smaller things, nothing bigger. And I've heard that elsewhere. So it's not just like a one customer problem. In fact, I do know of another customer that had a $200,000 a month, I guess you'd call it habit. All right, so what are we gonna do about this? We wrote a piece of code. We said we need predictability more than we need speed that has this as an impact. That's why the title of this was, are you a tortoise or a hare? If you're a hare and you need this to be done fast as possible without any worrying about any side effects, don't run our code. Don't use it. RocksDB is giving you the best possible solution. All right? But if you need something that is predictable, something that's not going to back up your whole cluster for 110 seconds, something that's not going to abort your customer's API or a client at 60 seconds, this is what you want. Okay? And that's what we're going to give you. All right. We have an external 2-part fix. The main thing is we needed this in a hurry, and we weren't ready to commit to our own fork of RocksDB, and so we did it outside. If you want the code, here it is. And most of the documentation is in this one, the rocksdbthrottle.cpp. And in that file, there are actually 2 things going on independently but using the same inputs. One, we are pacing the writes. We are making sure the writes come in. This is not the rate limiter code that you see delivered with RocksDB. It's something completely different. I'll describe that in a moment. And then we are prioritizing via the operating system scheduler, not the I/O scheduler, because if those of y'all have read the source code, you know there's an I/O scheduler prioritization piece inside RocksDB already, to help us pick which things need to go into compaction and who gets the time on the CPU. See this? Self-tuning to the current environment. Self-tuning means we don't change any parameters on a 4-core machine versus a 32-core machine. It knows what to do. It doesn't change any parameters if you've got, you roll out to a customer with the SSD drives or to a customer with SATA drives, or even better, you don't have to change parameters if one of your SSDs is starting to go bad, because you know that reduces the throughput by 1/3. It detects it and self-tunes. All right? So let's talk about the first part. How do we do dynamic smoothing? Okay, there is an object available to the end user called an event listener. You can get that. You can put it in your C code wherever you want to. And it gets information about when a flush happens, how long it took, when a compaction happens, how long it took. And so we use that to calculate a throttle. Then I do something a little not kosher. We can see the write controller, which is a read-only object. Yeah, but in C that means you just cast it to a read-write. And I basically take this sucker over. Yes, if it thinks you're behind, it will apply the RocksDB rate limiter, which is in this case, because of our environment, it is not useful. All right, I'm not saying it's a bad rate limiter. I'm just saying in our environment, doesn't work. And we use that write controller to pace everything that is coming into RocksDB. Okay, and let's go back and say the pacing logic works great. All right, all we're doing is saying what is the rate of the pace, and that's what we're overriding. How do we do this? How do we make it dynamic? Basically, we take all the compaction and flushes, and we say, how many bytes did you just compact? How long did it take? And the nice thing about that is, on a compaction, you're going to have the read that's coming in off the existing file, plus any other stuff going on in the operating system, maybe a big query that happens all the time, the reads, the disk speed itself, and then we're going to have all the times it takes to write, and we're going to have the CPU overhead of the compactions and the CRCs being calculated. So we're seeing how long it's really taking. And then we use that to say, dude, don't take them in any faster than that because we're just not cutting it. All right? Now, that's a very simple way to do it. Now, what are some other things that can happen that you're going to say, oh, but what about, okay, let's talk about that. There's the what about, well, you have compactions running simultaneously. It's true. And we're just saying, we're seeing what the interaction is between those and saying, even though that 4 are running, we're just going to use the rate of an imply of 1. Because the other thing we're not doing explicit calculation of yet is what is your write implication. All right, so basically I'm saying, I'm assuming write implication is 1, and I'm assuming that really there's only 1 compaction going on. All right, right now it's good enough. Can it get better? Absolutely. That's why you have revision 2. This is revision 1 code. Now, flushes we typically don't use because a flush only has a read from memory and write to disk. It doesn't have the read from disk component. So a compaction's got a lot more overhead, and we really want to use it. So the only time we use a flush is if there's no compaction data. And when will that happen? We're going to collect this information in 1-minute intervals. We're going to collect 60 of those over an hour and then start rolling. So we're keeping 60 rolling intervals. And when we calculate what the new throttle should be, before we apply it, we then put a smoothing algorithm against it. Okay, smoothing algorithm has a magic constant in it. I hate magic constants. Let me just tell you, it's 17. Okay, we take the current throttle, we subtract what the new throttle wants to be, and divide that by 17. Okay? If you've ever taken statistics, smoothing models have a constant like that. There are months and months in a previous piece of software that prove 17 is the right thing on a 60-minute interval. Okay? Even with this code that you're seeing here, I tried 15, I tried 30-second intervals, blah, blah. No, it didn't work. I'm going back with what is known. It's a magic constant. I apologize. Good luck if you want to change it. Okay? So that's how we're pacing. But pacing is only half the story because the other half is prioritization. Let's go back a couple slides. Okay, if too many of these happen, or if too many of these accumulate, we stop. If too many of the level zeros accumulate, we stop. But the current compaction selection logic doesn't really give a shit about that. It says, or the total bytes here, not the number of files, because the stop logic is on number of files. The logic for selecting is of what to compact next is based upon bytes. Well, I'm sorry, that hurts. I've actually sat there and watched as we approach the limit, which I think is 30. The given rate limiter that kicks in actually will increase the rate of stuff because it thinks, oh, the bytes are getting better. No, we're getting closer to 30. And we stop. Okay, so if these are our two key things in life, what should we do? Well, we should make absolutely positively positive that these get the highest priority. These get the next highest priority, and these get the third. RocksDB went beyond LevelDB and created two threading pools. One that's dedicated to this, thank you very much, seriously. But the second one has all of those, and these guys get lost sometimes in the midst of all these compactions. That hurts a lot. Because if we're off doing some other level and zero fills up, we stop. All right, so how do we fix this from outside LevelDB or RocksDB? Well, again, I cheat. We know when we have threads come through the event listener that it's actually the thread that is running the compaction that is talking to us. Okay, so those are the threads that are on the two pools. So there's one pool doing flushes. When that guy comes in, I set him to one off the normal scheduling priority. In Linux, scheduling priorities are the lower number is the highest priority. So I take the application, which is normally at 20, and I put the RocksDB at 21. All right, so now he's not going to have as much priority as all my networking threads that are keeping my cluster alive. You know, we use Raft and it has to talk to itself on a regular basis. And then I go and move the RocksDB compactions to 22 for level 0 and put all the rest of them at 23. So at any given moment, the guys I'm most worried about causing my system to stop have the highest priority on the system, but not over my networking, which is up here. Now, to be able to do this, 22 and 23, you have to understand one thing about Linux. Linux will always let you take your thread and make it a lower priority. It will not let you make it a higher priority. Unless you do this nice little thing here, which is go and set capsys nice capability, which go to the first source file that I listed up there. I've listed out the 3 steps you need to do to make that happen. If you can't do it because you can't get root on whatever machine you're doing, then this is what you're going to end up with. You're going to end up with the application thread still at 20, RocksDB flushes are there, and all compactions are at 23. That helps, but it doesn't help as much as this, because this is what gives you that clean graph yellow line that I was showing earlier. So we have now, and keep in mind, on a 4 CPU machine, you can't sacrifice one thread to be held around for this application. And you can't count on those 4 threads, if they're running compactions down here, to keep up with giving your flush threads time. This is how you say absolutely positively, this is the priority, I need stuff done so that you don't stop on me. So on a 4-thread machine, a 4-core machine, we'll still run 4 as the max background jobs. You say, hey, you can take the whole CPU, but my prioritization is what's going to keep you from killing the system. Tested, it works. I don't think I have another slide. I think we're done. I'm right. Okay, so any questions?
Thank you. So, any questions? Well.
So you talked about how you hacked RocksDB to do this, the prioritization of your I/O workload. Is this something that is configurable, or is there any pluggable thing that is missing in RocksDB that you'd have to? You cannot write a clean separation of a pluggable interface versus hacking the code and changing a read object to a write object and doing it that way?
The write controller object is not pluggable. If it were pluggable, this whole thing would be something that would just go along with you. So my request to you to make this more community friendly, make write controller pluggable.
Yeah, so quick one. I can infer that you need to train your throttling. Is that correct? So to have the effect of the throttling, do you have to have this in running for a while, or it just kicks in instantaneously?
That's a good question. Let me put the graph up and I'll show you. It's easier for me to show it from the graph. This right here is the training. The training ends very quickly. It is a self-training algorithm. It's a self-training algorithm. Yeah, and this is under heavy load. If you're under a lighter load, you don't even see these.
More questions?
Oh, in case you wonder, basically the philosophy is we're going to have as fewer tunables for our customer service people as possible. They needed to just plug in and run.
Okay, one last one, short one if possible.
I don't see how it will work with different sizes of machines, because it looks like you're battling a lost cause, because the I/O prioritization of your threads, you have different level of compaction, fighting for resources. You try to mess with it with changing the nice priority, but it depends on the workload. If all of those compaction priorities in level have work to do, then they'll need to consume CPUs and need to consume I/O. There's work in the page cache. You're definitely trying to do things, but the right way to do this is to have prioritization in user space. Make sure the database doesn't write above the maximum amount of parallel I/Os. And then you can really prioritize in user space and differentiate between compaction, reads, writes, commit log, and any other I/O consumer or CPU consumer.
Okay, so there's another derivative level DB called HyperDex, and that's how they do it. Now, this algorithm that we are using in Orango DB is derived off of an older algorithm. Have anybody here ever played League of Legends? Has anyone used the Starbucks app to order drinks? Okay, all of those have this algorithm underneath it. All right, this is proven. Okay, it does work. And it's basically because, yes, user space is the right place to do it, but that's more code and you got to go train those people. So we're just delivering a solution that they don't have to think about. It's like we're talking about how do you configure RocksDB? It's a big question. It's like, no, I'm going to start eliminating as many of those as I can. I just want them gone. I want self-tuning everywhere.
All right. Thank you, Matthew. So we have the last talk now by Stefan. And then